Okay, what do you prefer? Chalk. The choice is color chalk or color. There's one sort of prior benefit of the chalk is that I have 3 layers of that. Here there's only one here and one there, so 2 versus 6. If they both look good, don't vote. If one of them bothers you, vote. I mean, if one of them is significantly less clear than the other, voting for chalk, voting for dry board. Okay, chalk it is. Yun, could you please get me another box of color chalk? Because I'm going to run out very quickly. The 6th floor CSD office has a supply. Do you know where that is? 6th floor, there's a supply room. I'm sorry?
I don't know it. I've never been there.
Okay, it's the 6th floor in this part of the building. Right near, there's an open space where students hang out, like a lounge.
Yeah.
Just to the right of the lounge.
Okay.
There's an office supply. Ask me where the mail room is. It's where the mail room is.
No. Okay.
Yeah, 6th floor. Okay. So I'm going to use a lot of color today. How many of you heard of the Heisenberg uncertainty principle? Okay, how many of you kind of know what it's about? Okay, so the Heisenberg uncertainty principle is a very fundamental principle in modern physics. It's tied strongly to quantum theory. It has to do with the fact that you cannot know with complete accuracy both the position and the momentum of a particle. So the principle is expressed as a formula that the uncertainty in your knowledge of the position of a particle times the uncertainty in your knowledge of the momentum of the particle must be greater than some constant. So if you narrow down the accuracy, if you really zoom in on exactly where it is, you will know less well what the momentum is and vice versa. Okay? You don't need to really understand that, but on the slides that are online, I put a bullet that said the uncertainty principle of language modeling. So I thought I would explain what I meant by that. Last time we talked a lot about the heterogeneity of language and the fact that it varies along so many dimensions. Different genres, different audiences, different intentions, different media, different times, different topics. And when we build models that try to estimate language, the question is, what are we estimating? If you estimate general English, any kind of English, you're estimating something very heterogeneous, but you have a lot of data to estimate it. If you have a lot of data, that means you can estimate things very, very accurately. Things that happen very rarely, like a word that occurs once in 5 million, well, if you have billions of words worth of data, you can estimate its probability quite well. But if you want to estimate a very particular sublanguage, a very particular genre of, female teachers talking to children between the age 3 and 5 in the 1960s in the southern US, okay, that's one particular sublanguage. There will be far less data for estimating that. And therefore, your accuracy of estimation of whatever it is that you're trying to estimate in that language is going to be less good. So you see the trade-off here is between how pure is the sublanguage you are after? What is your target? Is it something very, very specific? Or is it all of English? Or is it something in between? That's one side of the trade-off. The other side of the trade-off, of course, is how accurately you're going to capture it. So if you want to capture a very specific subgenre, chances are you're going to have a limited amount of data. And so you will have to make that decision. And in fact, in the real world, when you have a real language technology application, you typically have in mind a particular genre. But there won't be very much data there. So you'll have to make the decision, and you might want to hedge your decision. Are you going to use only data from that one particular subdomain or subgenre? or you're also going to be using data from outside that's slightly different English, or whatever natural language it is. And there are ways of using both, in some sense. And we'll talk about that, of trying to benefit from both sides. But that's what I meant by the uncertainty principle of language modeling. So that's the end of that topic. And today I want to talk about probability theory and statistical estimation in general. So how many of you know what a random variable is? Okay, almost everybody. So let me define it for you anyway. A variable is a symbol that contains a value. A random variable is a symbol that contains not a single value, but a whole set of possible values with a distribution over them. Okay? So I will use red for a variable. A variable at any one time contains a single value. And that single value is possibly unknown. So you might not know it, but you know it's there. Unknown. A random variable. I used to use green for the random variable. I like the red and green, but I read that red and green is just the wrong thing to use when people have color vision deficiencies. So I'm trying to switch to blue. Let's see if I succeed. Random variable at any time contains a distribution over values. Distribution over multiple values. Over a set of values. I suppose the set could happen to consist of a single value, but the general case is over a set of values. Now I'd like to tie together probability theory and statistical estimation as two sides of the same story. So my story is going to be that there are some parameters, and parameters are going to be red. Parameters are variables of some sort. They may be fixed, they may be given, they don't depend on us, maybe they do depend on us. Whatever they are, they're fixed, whether we know them or not. Parameters are, I'll call them the most generic ways, theta 1, theta 2, theta k, or they could even be infinitely many. And the generic name for them is going to be theta bar. Bar here means an array of values. It does not mean expectation or mean or something like that. It's just shorthand for theta 1 through theta something. It's a vector of multiple random variables, so I'll refer to it abstractly as just theta bar. Then I have a likelihood function, which we've seen before. The likelihood function is of the form probability of some data given the parameters. I'm going to start coloring it. So the parameters are red. You can think of red as fixed. The data is blue. You can think of blue as variable. And the likelihood function likes to come with the letter L, but it is a probability. Now, I can do two things with this setup. The first thing I can do is, given the parameters, if somebody told me what the parameters are, given the parameters, Thank you.
For Catherine's, and she said we should ask Dana Houston for color shock.
Okay, but we got it. Thank you.
I have to return it after class.
You have to return it?
Yeah.
Okay, I will try to use it very gently. Ah, I broke it. Given theta, we can calculate, given the likelihood function, the probability of any possible set of data values. So it would be going from theta to data. I need to walk around with. And this is done by probability theory. And if you've taken a class in probability theory, which you probably did, then you had different examples of a likelihood function, and you were given the parameters. Let's say it was a binomial with the probability of head of 0.6, and you were asked, how likely is it that you will get 7 heads and 3 tails? Or it was a Gaussian with a given mean and a given standard deviation, which are the parameters of a Gaussian, and you were asked, give the likelihood of some events. What you did there is probability calculation. So in probability theory, theta is given and we calculate the likelihood of the data. Calculate likelihood of the data given theta. The flip side of this story is going from data to the parameters. In statistical estimation, you are given data estimate theta. Notice there's some asymmetry here. Here I say calculate the likelihood. Here I said estimate theta. The reason is, given some data, I cannot calculate what theta was in general, because multiple values of theta could have given rise to the same data. If I have 10 flips of a coin, not necessarily a fair coin, and 6 of them came down as head and 4 of them as tail, that is consistent with the coin being fair. It's consistent with the coin being 60% likely to fall on head and 40% on tail, or it's consistent with many other values too. Consistent in the sense that it doesn't contradict that possibility. So I cannot say with certainty what theta is. So the general story is I will not be able to know exactly what theta is. But I'm going to estimate. So what do I mean by estimate? I could mean multiple things. You want to suggest what could estimate mean? Like what kind of answer do I give? Well, you're giving me a specific recipe, but I'm saying what kind of answer am I getting? So behind your suggestion is give a guess. Give a particular value, like I think it's this one. Okay, that's called a point estimation. So estimation could be one of several things. One is point estimation. In point estimation, you're actually hazarding a point guess. You're saying, I think this is the value. And you could be right, you could be wrong. Chances are you're going to be wrong, in the sense that if the parameter has a range of possible values from, say, from 0 to 1, any continuous value, your chances of being exactly right are close to 0 usually, right? Because there are infinitely many choices between 0 and 1. Or you can try to assess how good your guess was, not by whether you're right or wrong, but how close it was to the right answer. And then you have maybe a better chance. So the way we would value the goodness of your answer is by how close? Close to the truth. What's another thing you can do? Sorry? Interval. You can give an interval estimation. You can say, I don't know what data is, but from the data it looks like it should be somewhere between this and that. Okay? We all did this in high school. So that is called interval estimation. And the measure here would be mostly were you right or wrong? Was the real value in there? Right or wrong? The third kind of estimation you can give is give a whole distribution over the possible values of theta. Give distribution over the values of theta conditioned on the data that you saw. So this is a posterior. Posterior because it's based on after you saw the data. So this is called posterior estimation, or just posterior. Can you apply here the notion of right or wrong? No, as long as your posterior assigns a non-zero value to any possible theta, then you will never be wrong, in a sense. You will never be proven wrong. But some posteriors might be proven to be better than others. Maybe you want it to be the case that when the actual value becomes known, your posterior has assigned it a relatively large value. So ideally, if you had magic in your hands, you would want a posterior that's like peaked right around the correct value. So just keep that in mind, that there are at least 3 different ways of estimating parameters. Best guess, interval, or posterior. Let's start with the last one. This is what Bayesian estimation does. I'm going to be talking a lot about Bayesian versus non-Bayesian statistics. Bayesians always hedge their bets. They never guess. They never put all their money in one thing. They always express their beliefs in terms of a distribution over all possible outcomes. Okay? So let's go back to Bayesian thinking, or Bayesian framework. Bayesian framework starts with the prior. A prior you can think of could be expressed as a distribution over the true values of theta. How likely is any particular theta to be a particular theta to be right. Now this, and also they like to write it as pi. Pi is just a convention for a distribution that is viewed as a prior. Now, this contradicts what I wrote underneath it, which is anything in red is fixed. It's not a distribution. Right? So this is where Bayesians change our rules. In non-Bayesian statistics, red is red and blue is blue, and you can tell them apart very easily. In Bayesian thinking, they don't like red. They convert all red into blue. Namely, Bayesians look at fixed but unknown values as if they were not fixed, as if they came from some distribution. Another way of thinking about it is to say that non-Bayesian statistics says we live in this world, there are some parameters in this world, they're fixed, we don't know what they are. A Bayesian would say, well, we don't really live in this world, we live in all possible worlds, and we are just one of all possible worlds, and when all the possible worlds were created, there was some distribution of values over them. It's not a mathematical difference, it's a subtle philosophical difference, but you will see it coming again and again. Is what we're after fixed but unknown, or is what we're after something that comes from a distribution?
Should this be blue then?
Yeah. So in the Bayesian world, it becomes blue, yes. So the very fact that there's a distribution over it implies that it has to be blue. Okay, that it changes, that it has a so it's really, and now in the Bayes world, everything will be blue, so maybe I'll just use white for this. So another way of saying it is that in Bayes thinking, parameters are treated, and sometimes even thought about, as random variables. Not just the data, but the parameters. So in real extreme pure Bayesian thinking, data and parameters are kind of the same creatures, which can freak you out the first time you hear about it because it's against your normal thinking. But bear with me. Then there's a likelihood function. It would be likelihood of the data given the parameters. Then there's the posterior, and there's all the things that we've discussed. So I will not say much more about Bayesian estimation because we did already. The Bayesian formula is really all there is there, except to say that Bayesian estimation takes a prior, which is f theta, and takes it through the Bayes machine with the help of data and the likelihood function. Oh, the likelihood function is conveniently right here, so I'll just put this arrow. And out comes the posterior. Which is P of theta given data. So what comes in comes out. So this is the machine. This is the Bayes machine. Things come in this way and come out that way. The things that come in and go out are of the same type. They're both distribution over possible true values of theta. You could call it distribution over the true state of the world. We don't know which world we're in. We're just thrown into a world that was created with some distribution out of all possible worlds, and we're wondering which world we're in. And we start with a prior notion of what's the likely values of the world we're in. And after we saw some data, we have a modified view of it. We've changed. We've become wiser, hopefully. We know more. This is more smarter or more likely to be accurate than this. What did we use in the process of getting there? We used data, but importantly, we also used another assumption. We used the assumption of what the correct likelihood function is. Bayes' framework can be shown to be optimal in some sense, but under the condition that the likelihood function is correct. If you try to use Bayes reasoning but use the wrong likelihood function, you may diverge and get worse and worse answer rather than better and better answer. So the typical picture that you get when you start with a prior, let's say that theta can take on values between 0 and 1. Right? Theta is a parameter. It could be any range and could be more than one parameter. But the simplest case is take a value between 0 and 1. You can think about it as the probability of head or anything like that. A prior could be anything. Specifically, it could be a uniform prior. So this would be 1. So this is a density function. It's uniform. And after you saw some data, it might change to something like this. And after you saw more data, it might change to something like this. And after you saw more and more data, it might change to something like this, and so forth. If everything goes well, as you see more and more data, your posterior should become peaked and hopefully peaked in the right area, the right location. And again, if everything goes well and if your likelihood function is correct, you can prove that as the amount of data goes to infinity, your posterior becomes goes also to infinity in the sense that its width goes to 0 and its mean goes to the value, the correct value, if your likelihood function is correct. But that's only if you have infinite data. If you have infinite data and your likelihood function is correct, then your prior, in a sense, doesn't matter. It does matter in extreme cases, namely, if you started with a prior of 0 here, then the posterior could never be more than 0. Right? If you think about Bayes' formula, the posterior is proportional to the product of the prior and the likelihood. So if either the prior or the likelihood gave you 0 for some values of theta, the posterior will have 0. So if the prior gave you 0, the posterior will have 0, and then as you get more and more data, you will stay with 0. So if you started with the value of 0 on some part of your parameter range, you cannot recover from that. But as long as you didn't make that mistake, as long as you assigned some non-zero probability to every possible value of theta, as you get more and more data in the limit, which prior you started with would not matter in the limit. Any questions about this? All right, the more interesting case is the non-Bayesian case. Or at least more interesting in the sense we didn't talk about it that much. So for this, we're going to do point estimation first. Point estimation. And point estimation is necessarily non-Bayesian. Non-Bayesian is often called frequentist. Frequentist statistics is non-Bayesian statistics. There are basically two schools of thought in statistics. One is called Bayesian, the other one is called frequentist. They are quite at odds with each other at times, both theoretically, intellectually, but also in terms of dogma. I mean, there are people who are, die-in-the-wool Bayesians, and they just don't believe in any of this non-Bayesian nonsense. And there are people who are frequentists, and they don't say that Bayesian statistics is not valid, but they each have criticisms of each other, and we're going to discuss some of these criticisms. I should mention that I would say frequency statistics currently rules the day in terms of methods that are used in practice, in practical applications, for reasons that we will discuss later. And therefore, most statistics departments in the world, certainly in the US, you would say are frequentists in some very rough sense. There are a few that are very heavily Bayesian, and Carnegie Mellon is one of them. Luckily, Carnegie Mellon is not a dogmatic place. So actually people here, most of them, don't curse and badmouth the frequentists. On the contrary, they actually see the benefits of both sides and If you talk to Larry Wasserman, the guy who wrote that Hot Pink book, he would happily give you arguments in both directions and tell you that sometimes he would use one, sometimes would use the other. So he's sort of a non-committed. Others are slightly more religious about it. But it is a pretty lively debate, sort of intellectual and practical debate. And it does have some real pragmatic implications, which we will touch on. Okay, so point estimation is your given data and you kind of have to guess. You're not guessing because you're basing it on the data, but you have to choose, maybe is a better word than guess. You're forced to choose a point, and we will call it theta hat. Theta hat is the standard statistical notation for the estimate of theta, of the parameter theta. So we're going to base theta hat on the data, and we know that the data is a random variable, right? It's in blue. Well, if it's going to be a function of the random variable, a function of a random variable is also a random variable, right? Therefore, my estimate is a random variable, and I ought to write it in blue. This is really important because the thing I'm trying to estimate is red, but my estimate of it is blue. The thing I'm trying to estimate is the true probability. Now we left Bayesian aside. Now we believe there is one true probability theta. We just don't know what it is. We believe it exists. Maybe somebody else knows it. Maybe we'll find it out at the end. It is there. We just don't know what it is. We're going to estimate it by some procedure that generates data, and we're going to take the data and crunch on it and come up with an estimate. But since the data is a random variable, the data we got today would be different than the data we get tomorrow, even though the true theta didn't change. So our estimate is necessarily going to be a random variable too. It would give us different values on different days. Let me make it very concrete. Suppose you're trying to estimate the probability of head of a coin, which is not necessarily fair. So it's not necessarily 0.5. Let's say the true probability of the coin of being head is 0.7, 70%. You don't know it, but I know it. Okay? You flip the coin 10 times, and you got 6 heads and 4 tails. You might be tempted to guess, as your estimate, probability is 60%. That's not a bad guess. It's a relative frequency. You flip the same coin again tomorrow, and you'll get 5 heads. You flip the same coin again the day after, and you'll get 9 heads. Right? On different experiments with the exact same coin, with the exact same truth, the truth is 0.7, same truth, you'll get different data. And therefore, your estimate, if you use the relative frequency estimation, would be different. That's the sense in which I mean that the estimate, or an estimator, is a random variable. It has a distribution. This is really an important fundamental fact. Estimators are random variables. I used interchangeably the word estimator and estimate. What I mean is the function, when you think about it as a function that you plug in data and you get out a value, it's an estimator. When you have a particular set of data you work with and you plug it into the estimator, the output of that function is a particular estimate. So the estimator is a random variable. Of course, an estimate is just a number. It's not a random variable. Random variables have all sorts of properties. Let's review some of them. We already said that the function of a random variable is also a random variable. Right? You can add constants to random variables. You can multiply them by other constants. You can add 2 random variables. You can take any function. if x and y are random variables, then something like e to the x squared plus 2y cosine xy is also a random variable. Over a different set of values with a different distribution, but it's a random variable that's well defined in terms of these random variables. So any way of combining random variables creates a random variable. Specifically, two properties of random variables that we care about is mean and variance. So the mean of a random variable and the variance of a random variable one qualification. Until now, we didn't say what the values of the random variable have to be. We assume they're going to be numerical, but they don't have to be. Random variables can have distributions over colors. For it to have an expectation and a variance, they have to be, the values of the random variables must be numerical. So here's an example of a random variable, a perfectly good random variable that does not have an expectation. Let's random variable x come from a distribution over red, blue, green. And let's say it's 0.4, 0.3, 0.3, just arbitrarily chosen distribution. This is a perfectly good random variable, but there's no sense in which it has an expectation, right? And what I said about the function of random variables, well, we have to define what it means to take a function over colors. So just to keep it in your mind separate, random variables can be over things that are not numerical. But in the case of estimation of parameters, we're going to assume that they're numerical, and therefore they typically have an expectation and a variance. Some extreme cases, they might not have a variance, maybe infinite variance, but we're not going to worry about those. All right, so this is a random variable that tries to estimate, to get at the true value theta, which is fixed. So now my question to you is, what are desirable properties of the estimator? I didn't tell you what my estimator is. I just said any function of the data is potentially an estimator. And there are infinitely many functions of the data. What are desirable properties of estimators? I'm sorry? Since we didn't introduce what bias is, can you express it in other terminology? Okay, so maybe you mean bias in the everyday sense, that they shouldn't consistently overshoot the target or consistently undershoot the target, right?
They should minimize the error in some sense of the data to the true value of theta.
Okay, so let's start with the first notion of not overshooting or not undershooting. If you have an estimator that every time you use it, it turns out it gives you an answer that is less than the correct answer, then there's something wrong with it. It is consistently underestimating the target, and that kind of suggests a way of fixing it by increasing whatever it gives you, adding something to it, right? Same thing in the other direction. If you have an estimator that more often than not overshoots or gives you an answer that's higher than the truth, you would feel somewhat more satisfied if the estimator doesn't overshoot or undershoot in a consistent, like all the time. So maybe one way of capturing is to say that it overshoots as often as it undershoots. You cannot realistically expect it to always be correct, right? You realize that. It's not always going to be correct. But you don't want it to be overshooting more than undershooting. It's not exactly maybe what you want, because if it overshoots more often than it undershoots, but when it undershoots by a lot, and when it overshoots by a little, maybe you want the average overshooting to be the same as the average undershooting. So that's the first property that I would like to capture, and I'm going to capture it by saying that the expected value of the estimator should be right on target. So desired property 1, desired properties of estimators. First desired property is that the expected value of the estimator should be exactly the true value. Now let me put colors on it. The true value is red. It's a fixed constant. Unknown but fixed. The data, of course, is blue because it's a random variable. On different days you get a different sample of data. What's this? Sorry? Blue or red? Blue. Because it's a function of random variable, so it's random variable. What's this? This is red. So an expectation is a function that takes us from blue to red. Because what does expectation do? It takes a distribution and converts it into a single number, a number that does not change. Right? So whenever you see the expectation operator, it takes its input, which has to be blue, and converts it to an outcome, which is a single number, which is red. Which is why we can make that statement that red equals red. Otherwise, there would be something wrong here. We cannot compare red and blue. Blue is a distribution. Red is a fixed number. Now, whenever there's an expectation, you need to ask it, to make sure that you understand what an expectation is, you need to ask yourself expectation over what variable and according to which distribution. So what variable is the expectation taken under or over? Data, exactly. It's expectation over data. I'm going to write it here explicitly. It's expectation over the data. And expectation based on which distribution? I'm sorry? Yes. So what letter would you use for that? It's the data as distributed according to the likelihood function with the true parameter. That's what we mean by the expectation. Expectation is like summing over all possible values of the data sample, all possible data samples we can get, each data sample weighted by how likely it is to be generated, assuming the true value of theta. So I will not always write it, but you have to always make sure that you know when there is an expectation somewhere, that you know expectation over what variable under what distribution. So this is a desired property. I'm going to change it a little bit. And instead of saying this is the property, I'm going to say I would like the property to be that the difference between them be small. So in the extreme case, it should be 0. And I will call the difference between them the bias. Bias of this, this particular estimator. Remember, this is an estimator. This is a particular function. Now, what color is the theta? Theta hat? Theta hat is blue. What color is the word bias? It's red. It's a single number. So the bias of an estimator, written shorthand, the bias of an estimator is the expectation of the estimator minus the true value of what it's trying to estimate. This is the same thing as this, and this is written with great detail. And specifically, an unbiased estimator is an estimator that has zero bias. Namely, its expected value is the correct value. This is just one desirable property. Let me also give you a graphical interpretation of it. If the true value, again, the example taken from theta being between 0 and 1, if the true value is 0.7, so this is the truth. And after seeing 25 data points, my estimator gives me, what does it give me? It gives me a value for a particular set of data points. It might give me this value. But for a different set of data points, it will give me this value. And for another data point, it will give me this value, and this value, and this value, and so forth. And if I apply it many, many times, either many, many times, or I just do it in theory over all possible data distributions, I will get a distribution here. I want the mean of this distribution. This is the mean of this distribution. This is the center of gravity of this distribution. I would like it to be as close to the red line as possible. That's not the only property I can specify. I could specify that I want the maximum of this distribution to be close. But there are reasons I want the mean. So remember that estimators are distributions. The distribution over an underlying space of data samples. And this is based on a particular set of, let's say, data is, the size of the data is 25 samples. If we didn't have 25 samples, if we had 100 samples, this distribution might look different. Right? For a fixed sample size, I get a distribution over the possible outputs of the estimator. All right, so my first desired property is that the mean of distribution be as close to the true value of theta as possible. What other desired properties might I have? The variance is minimal. So here is one distribution that has a mean. Let's say its mean was exactly on target, exactly here. So this particular estimator is unbiased. Its mean is exactly on the correct value. And here's another one. It almost always, for almost all data sets, it comes right to the right area. And let's say it's also unbiased. So its mean is also in the same place. So you have two distributions with mean, both of them exactly the same mean, so both of them are unbiased. But one of them tends to give you answers that are much closer, on average, to the correct answer than the other. So you would prefer that, right? The sample size should be the same for it to be a fair comparison. Yeah, for the same sample size, you might have two distributions, two estimates that result in two distributions, both of which are unbiased, but one of them is concentrated much more around the correct answer. Or they might both be biased to the same amount. Or, what's more complicated, is the one that has a smaller variance actually is somewhat biased. Let's say the variance is it's like this. So it's like biased low. This one is not biased, but it's very broad. So now you have a trade-off between a distribution whose average is more correct, has a lower bias, maybe zero bias, and a distribution whose average is less correct, but its spread is smaller. This is known as the famous bias-variance trade-off. That would happen a lot, where we have to choose between two distributions, and one of them would be better along that measure, the other one would be better along the other measure. Which one should we choose? That depends on our goal. we'll have to start from the end, from what it is used for, and from that derive our measure of goodness, and that would tell us something about how to weigh bias and variance against one another. One very commonly used measure of goodness is mean squared error. So what is mean squared error? Mean squared error is a measure of the goodness of an estimator relative to the true value. So I'm going to go back to my colors. This is blue. I will sometimes not bother with putting here the parentheses and the word data in it. But I'd like you to remember that whenever there's a hat, there's data hiding in there. It's a random variable that depends, is a function of the data, which is random variable itself. So there's data in there. The mean squared error looks at the squared of the error. So let's start from the end. First of all, error is defined as the difference between what a particular estimate gave you, one particular estimate, and the true red value. That's the error. Squared is take that and square it, which means that the further you go, the significantly more impact it has, and also that it ignores whether it's an underestimation or overestimation because it's squared. And then the mean part says take the expectation of that over all possible data samples. So this is defined as the expectation of the value of the estimator on some data, a particular estimate, minus the true value squared. What is this expectation over? It's over data. And under what distribution? Under the true distribution, the true likelihood of the data given the parameter. I will not even bother with the bars. The bar is only there to remind you that it could be more than one number. It could be a set of numbers. I won't bother with that. All right, let's put colors. This is red, right? This is blue, right? So therefore this is blue. So now we have a blue thingy minus a red thingy. Is that kosher? Is that legal? Can you subtract a constant from a random variable? Yes. A random variable that is numerical random variable, which is all we're dealing with here. Yes, you can subtract a red from a blue. What do you get when you subtract a red from a blue? Blue, right? So there's nothing wrong with subtracting, multiplying, adding reds. It still remains a blue. Therefore, these parentheses are blue. Now we square it. What do we get when you square blue? Again blue. It's a function of a random variable. And therefore, inside this thing is all blue. Now we take the expectation. What do we get? Red. So the mean squared error is a fixed number. Given the particular estimator, given the estimator function, it's a fixed number. God, or whoever knows the true value of theta, can calculate it. This is a measure that is often used as a measure of how good the estimator is. And one nice thing about it is that it's very easy to express it as a function of the variance and the bias. This is known as the bias variance breakdown or bias variance. No, trade-off is when you trade one against the other. That's true even if they don't use mean squared error. I don't know. I'm sorry? Decomposition, thank you. Bias variance decomposition. So let's do that. mean squared error of theta hat theta. I may or may not add colors. You can add colors later to is the expectation of theta hat minus theta. I'll write it here. Squared. I just copied what was there. I'm going to play some algebraic tricks here. I'm going to add and subtract the expected value of theta hat. So what should I call? Now since I don't use bars anymore, I could use a bar, but it'll be confusing. So I'll just call it E theta. Okay? I can do it like this. It'll be a little easier. E of theta. Just the expectation of theta. It corresponds to the mean of this distribution. Is it red or blue? It's red. Okay? So I'm going to subtract E of theta. I'm sorry, it's E of theta hat. You should have corrected me.
So is it an expectation of a variable just itself? Or of a variable?
An expectation is a random variable in the sense that it's a function of a random variable, but it is what's the word for it? It's a special case where the distribution is a single number. So every red is also blue in the sense that it's a distribution that has only one value with 100%, right?
Right. Well, I was trying to say if you take expectation of a variable like theta, isn't that just theta because theta is
Yes.
unknown?
Okay.
Value?
Yeah. If you take an expectation over a constant, you get back the same constant. Yes. But that's not what I meant to do here. What I meant to do is expectation of the estimator, theta hat. So I subtract theta hat, and I'm going to add E of theta hat.
So you're taking the expectation of something with an expectation inside?
Yeah, and you can do that. I mean, it's kind of silly, but I'm doing it so that I can break it up algebraically. Okay? Yeah, E of something is same as E of something. Taking the expectation operator more than once doesn't do anything. This property is called idempotency. E, the E operator, is idempotent. It means applying it once is the same as applying it multiple times in a row. After you apply it once, it doesn't do anything anymore. Can you think of other example of an idempotent operation? I'm sorry? Absolute value. That's great. Sorting. Once you sort once, sorting again does not change anything. But it's not exactly what I'm doing here. I'm sticking it inside this operation. So far, I'm completely legit. I just add and subtract the same thing. Now I'm going to group them. I'll call this A. I'll call this B. So I have E of A plus B squared. I forgot to put open parentheses here. So this is A plus B squared. So this would be, A and B are random variables. So E of A plus B squared is E of A squared plus B squared plus 2AB. This is completely legitimate. It's just algebraic manipulation. This is equal to E of A squared plus E of B squared plus 2 times E of AB. Notice I did not write E of A times E of B. That would not necessarily be true. So this is something about the expectation operator. It is additive. It is linear. It's a linear operator. So expectation of any weighted sum of random variables, if the W's are just reals, and these are random variables, any number of random variables weighted together is the same as the sum of the weights over the expectations. So specifically for one or two variables, E of 3x is like 3 of E of x, and E of 3x plus 2y is like 3 of E of x plus 2 times E of y. But E of x times y, when x and y are both random variables, is not necessarily E of x times E of y. Sometimes it is, sometimes it isn't. So we cannot break apart a multiplication of random variables, but we can certainly take constants out. So this is what we did here, and we are left with this. So now let's look at E of a squared. This is E of theta hat minus E theta hat squared. This is E of theta hat squared, right? So now I'm going to open it again. Now here is something to
Can you swap them before doing the square?
swap these two?
Yeah, then you get expectation minus.
Right, right. Oh, you're right, I should. Let me do that. Right. But he's right, I should swap it so that I... okay, so let me just swap them. Thank you both. E of theta hat minus theta hat. Yeah, here I don't need to break it up. You're completely right, and here's why. Once I introduce colors, it becomes a lot clearer. So this is red, right? This is blue. I'm sorry. You guys should correct me. Show me that you know what I'm talking about. This is not... No. That's the other side. You got me, you led me in the wrong direction. This would be the bias. This would be the bias.
Yeah, but
Because
EA squared is the variance.
okay. All right. Oh, so you're right that I don't need to open it, but not for the reason I thought.
Yeah, you should have to
Okay.
order.
Okay. Thank you. Okay. So what is this? Where's the head? Thank you. Yeah. Keep me on my toes. And we might as well give it a color. No, this is not wrong color. I guess I'm on a streak here. Okay. Hat, and this is red, and this is estimator, so this is, and blue minus red gives us blue, so this is blue, and squaring it still keeps us in blue, but taking the expectations make it red. So in the end, this will become a number, but everything inside is blue. Now, what is this? This is not the same as what we saw. Compare this to this. They look very, very similar, so look at them carefully. They're both expectations of something squared, and that something is the random variable that's the estimator minus some red quantity. But the red quantity is different. Here, it's the true value, and here, it's the mean of the estimator, which may not be the same. What's common to both of these, they're both called second moments. A second moment of a distribution is the expected value of the value of the random variable minus some, I don't know what to call it, mu squared. Second moment of a random variable x about mu. It's the second moment of the random variable x about some point mu. But a second moment could be, it's second because of this thing. A second moment could be about many different points. When the second moment is about the mean of x, it's called the variance. When the second moment is about the true thing you're after, it's called the mean squared error. So this, as Yoon pointed out, is the variance of the random variable we're after, which is theta hat. So we have E of A squared, E of B squared, and plus, this is plus, 2E of AB. E of A squared we decided is the variance of the estimator. All right, let's look at E of B squared. B squared is E of theta hat minus theta. So it's E of theta hat minus real theta, and it's squared. Again, once you put color on it, it becomes a lot clearer. Theta is the true theta, which we don't know. Theta hat is a random variable, so it's blue. But when you take its expectation, the whole thing becomes red. So this is red minus red, which means what you have in parentheses is red. You take the square of that, it's also red. So what you have in the squared bracket is also red. And it turns out that this E operation is unnecessary, because you're applying it to a constant, you get a constant too. But more interestingly, if you look at this, this is our definition of a bias. Bias of theta hat. Right? We define the bias as the difference between the expected value of theta hat and the true value of theta. So since this is the bias, when you square it, you get the bias squared. So this is bias of theta hat squared, or bias squared of theta hat. The last thing we have left is the 2 times E of AB, A times B. But now notice that we found out that B is a constant. We found out here, see the B squared? This is B. This thing before the squaring. This is B. And we found out it's red. If it's red, it can be taken out of the E operation. Right? So if I just, I'm sorry, this is B. A is still blue. And therefore, we can legitimately say that this is equal to 2 times B times E of A. A is blue, B is red. What is A? Let's see. We have 2 times B, which is the bias, times E of, what's our definition of A here? Theta hat minus E of theta hat. E of theta hat minus E of theta hat. Again, once you put the colors on, it becomes very clear. E of theta hat is red. This is still blue. But because this is red, it's a constant. The expectation of a random variable minus a constant, you can take the constant out of the expectation operator. So it becomes the expectation of theta hat minus the expectation of this, which is the same as the expectation of this. So it's the expectation of theta hat itself again. Right? So this we already knew was red. And now this becomes red. And guess what? They're the same. So the whole 2ab thing goes away. We have a 0 in there. This becomes a 0. So we're left with the a squared and b squared. And therefore, the final answer is the mean squared error of an estimator with regard to the true answer, that's what mean squared error means, equals the variance of the estimator. Variance does not depend on the true answer. Variance is the property of the estimator of the distribution itself, plus the bias of the estimator. This time it does depend on the true answer, because bias is relative to the true thing, right? So, I'm sorry, bias squared. So a short way of writing it is MSE equals var plus b squared, or v plus b squared. So that's the famous bias variance decomposition. And again, you might want to put colors on it. So this is red. What else is red? This is not red. This is red, right? This is blue. This is blue. The bias operator takes a blue, a distribution, an estimator, and a target, and returns a number. So it returns a red. And if bias is red, its square is red too. The variance operator takes a distribution and returns a single number. And you have red plus red. This is red too. I should have warned you to bring color pens. I'm sorry. But it will be great practice to go over the uncolored, color in. Because, of course, in the real world, you'll have all these formulas, and it will not be clear what is what. And when people write sloppily, sometimes they write it wrongly, and they will equate blue here and a red there. And it's good to keep in mind, what are you talking about? Are you talking about a distribution or a value? Questions? So we talked about what an estimator is. It's a function, which is a random variable, and two desired properties of an estimator: having as small bias as possible and having as small a variance as possible. An estimator that has no variance, has no bias, has a bias of 0, is called an unbiased estimator. And other things being equal, it's generally desirable to have an unbiased estimator. But it will not always be possible. And when it is possible, other things may not be equal. And you may need to choose between trading off bias versus variance. One particular way of trading them off is if what you care about is the mean squared error. If what you care about is mean squared error, if that's your measure of goodness, then this is the right way to trade them off. So you can actually look at a whole series or set of estimators and choose the one that maximizes or that minimizes the MSE. These are not the only properties that are desired. So let's try to think of others. Good. Good. One other sort of obvious desired property is as you get more and more data, you want your estimator to converge closer and closer to the truth. In the limit with infinite data, you want your estimator to converge to the correct answer with probability 1. So there, you have to define it very carefully because convergence with probability 1 is not the same as regular convergence. For example, even if you have a very good estimator and you have infinite data, there's always some non-zero probability that your infinite data is going to, non-zero but goes to zero probability, that your large amounts of data would be atypical data. So there's always some non-zero probability of, for any finite sample, some non-zero probability that you will get a bad answer. But you can define it carefully using calculus, using the definition of convergence and probability. And what you want is the property that your estimator, as it applies to data, as the amount of data goes to infinity, you want it to converge to the true answer. Or actually, what you want here is a delta function over the true answer. Okay? A delta function of the true answer is, remember that this is a distribution. But as you have more and more data, you want the distribution to be more and more and more peaked right around the correct value. In the limit of a peak distribution around the simple value is called the delta function. It's a function that is 0 everywhere, infinite on this value, and integrates to 1. And you want this convergence in probability, so you put a little p here. So the exact meaning of this is not important if you didn't take the right level of calculus, but the take-home message is you want the estimator to be consistent. Namely, with enough data, it should go in the right direction. So this is called consistency. Or be more accurate, you should call it asymptotic consistency. There's one more property that we don't have time to talk about. We'll talk about next time. Well, there are many other properties, but there's one more property I want to mention, and it's efficiency. Namely, how fast do you converge to the right answer? So we'll talk about it next time. And I had to mention a few things. Some of you are not on Piazza. Can anybody who doesn't know what I'm talking about or who knows what I'm talking about but didn't get on Piazza raise their hand? Okay, will you please send mail to Yoon and ask him to add you to the Piazza. So we're doing all the communication of the course on Piazza, which is really a much, much better way of doing it than by email. So it's just a web service, a very nice service. And once you get, you will get, after you write to Yoon, you will get an invitation to join. Once you join, you'll figure it out. It's very simple. Anything else? Homework. Due Wednesday, right?
No, place the homework.
Oh, the hand-in directory.
So I have created them, but I have heard feedback that they don't have access. So can I visit you sometime this afternoon?
Sure. Sure. Around 3:45 or 4, would that work for you?
4:30.
That's fine. I think that's fine. Let me check. Okay, thank you.